we go all the way down to the center of the planet, a depth of about 70,000 kilometers. We have a temperature. Temperature is actually going to reach 25,000 Kelvin, and the pressure will be on the order of about 60 million atmospheres, 6 times 10 to the 7th atmospheres. The magnetosphere, which is the magnetic field that's actually being produced by Jupiter, it's approximately 30 million miles across and about 6 million times more, a greater volume than the magnetosphere of the Earth. Strength is actually something on the order of 20,000, approximately 20,000 times greater than the Earth's magnetic field. And this was measured by the Pioneer 10 spacecraft. On the sunward side of the magnetosphere, and this where it only extends 3 million miles from the planet, as opposed to 30 million miles on the outer side, this is referred to, this particular point is referred to as the magnetopause. So you've got, if here's the planet, you've got the magnetic field going out a relatively small distance and then a much greater distance on the other side of the planet. It's extending out 30 million miles and then only 3 million miles on this side. Still a pretty long extension, but so this line over here is called the magnetopause. That's all one word. I'm going to hyphenate it, pause. So the tail end, it's almost like a cometary tail, actually extends out beyond Saturn's orbit, and we can kind of get an idea of this. Pioneer 10 was actually able to look at this tailing effect. It's actually due to the solar wind, so we can actually find out where this ends, at the point where it ends. So Saturn is somewhere out here, but it's going to end actually out beyond Saturn. Saturn has its own magnetosphere, but Jupiter's magnetosphere, there's a point at which it can no longer be measured, and that's what we're really looking at, are these ionized particles that are streaming out towards these planets from the sun. The 4 largest moons of Jupiter, which are Io, Europa, Ganymede, and Callisto, they're actually, those 4 are known as the Galilean moons, because these were the ones that Galileo was actually able to observe with his rather primitive telescope. There are a total of 63 moons of Jupiter that have actually been observed to date. The other 55 satellites beyond the 4 really large ones, and then there's 4 other smaller ones, medium-sized satellites, and the remaining 55 satellites are quite small, probably 10 kilometers or less in diameter, and they lie well outside the orbit of the Galilean moons. So the Galilean moons, the last one is 1,880,000 kilometers, that's Callisto, from Jupiter. Ganymede, which is closer, is a little over 1,070,000 kilometers. Europa, 671,000, and Io, 422,000. I kind of remember the order of these moons using a little mnemonic, which is I eat grapes. This is my own mnemonic. There's probably other ones, but you can make up anything. I eat grapes cold. So that way I can remember what the order is. So the closest one is Io, then this is Europa, Ganymede, and Callisto. So if you can remember the names of the planets, of the moons, the major moons, but you can't remember their order in here's Jupiter over here, and this is going to greater distance from the planet. If you remember that silly little mnemonic, I eat grapes cold, then you can remember what the order of the planets happens to be. So within these other four, what I would call medium-sized satellites, are actually within EO's orbit, which is why we weren't able to see them from the Earth, because they are considerably smaller, and they actually orbit closer to the planet's surface. The largest of these is Analthea, and Analthea is 260 kilometers in diameter and was discovered by E.E. Barnard. We'll hear more about him later. There's something called Barnard's star that we're going to talk about in a later lecture. And this is the same Barnard that Barnard's star was named after. And the other three satellites, besides the one that was discovered by Barnard in 1892, were found much earlier by Christian Huygens. And Huygens was, I don't remember when Huygens lived, but I think he was, I'm sure he was before Barnard's time. Anyway, and I mentioned that the other 55 satellites are small, very small. I want to talk a little bit about some of the major satellites, however. So Io is the closest moon. It's very geologically, it's the most geologically active of all the moons, and possibly the most geologically active of all the objects in the solar system. It consists of a rocky mantle, and it's got a core that's composed of iron and iron sulfide. I don't know specifically what the composition of the iron sulfide is, but it's considered to be an iron sulfide core. Io has a very thin atmosphere of sulfur dioxide. It's probably not a permanent atmosphere. It's probably sulfur dioxide that's actually being put into the atmosphere by a lot of the volcanic activity that's taking place on the surface of the planet. It's got a kind of an orange-yellow color, which may be due to sulfur and some sulfur compounds. The other interesting thing about Io is that as Io orbits Jupiter, as Io moves around Jupiter, it's moving around this enormous magnetosphere. At the point where Jupiter is actually orbiting, it's producing what is actually a magnetic torus around the planet. So a torus is kind of like a donut. So this would be like if you had a cylinder and you bend it around into this shape here. So that's got a toroidal shape. And this torus, what it's actually composed of is a plasma. So this is a very, very highly charged gas, and it's actually caused, though, so you don't have this elsewhere, but you actually have this magnetic torus, this magnetic plasma. It's heated up, and it's actually being driven by the movement of Io through the magnetosphere, and that's the only place where we actually see that. We don't see it in any of the outer Europa or Ganymede or Callisto. We don't see this torus forming out there, because the field is weakening as we get further out into space. Europa, if we actually look at its composition, it's similar to Io's composition. It's got a smaller core, but what's interesting about Europa, something that we have on Europa that we don't have on Io, is that there's a crust present that's actually composed of water ice. And if we go below that crust, it's believed that there is liquid water underneath that. So above the mantle, this water will go all the way down to the mantle of the moon. And the Galileo probe actually showed what appears to be something that looks like an iceberg on the surface of Europa. So this is really remarkable. And the ice is probably several kilometers thick, and it may be as much as 100 kilometers deep there could be a 100-kilometer deep actual liquid ocean below this. Now, some of this is speculative, but this is what scientists currently believe. There are also relatively few impact craters on the surface of this icy moon, and this indicates that it's continuously being reshaped, probably by water that is actually welling up from fissures in the surface of the planet and then immediately freezing. So Io is another place where people might want to look at some point in time for some form of life. It's still a very, very hostile environment, but it's going to be very, very cold. But nevertheless, we have found, surprisingly, on our own planet, we found life in cold regions where it was not previously thought that life could actually exist. And this might not be a terrestrial, anything like terrestrial type of life as well. Europa's core is also an iron sulfide core. It's comparatively smaller, though, than the core of Io. So even though Europa is a little bit smaller in diameter, Io's diameter is 3640 kilometers and Europa's 3130, its core is actually considerably smaller than that would be expected if the two objects had relatively the same size cores, the same percentage size cores. Ganymede and Callisto are both similar to one another. Ganymede has markings that look very much like the Maria and Highlands of our moon. Ganymede has a crust of ice. It's got a rocky mantle that is and a small iron sulfide core. Ganymede turns out is a little bit larger than Mercury at 5270 kilometers in diameter, making it the of the four moons of the four large moons of Jupiter, making it the largest moon. However, if we look at the densities of all four objects, Io's density is 3,500 kilograms per cubic meter. Europa's is 3,000. Ganymede's and Callisto's are only 1,900 kilograms per cubic meter, so much lower. The Ganymede is believed to have a slushy liquid water interior. Callisto is much more heavily cratered than Ganymede and shows a series of concentric ridges around the largest crater, which is known as Valhalla. And this is believed to be the crater Valhalla, of course, was formed by a collision with a large, perhaps meteoroid or small asteroid that struck the surface. This created a series of ripples. If we looked at that, it actually created a series of ripples in the somewhat liquidy surface, which immediately froze to give these, the ripples before they could actually dissipate. Kind of like when you throw water into a pond, you get these ripples. But this froze and gave this particular pattern that we see now. The entire moon appears to be an ice, unlike Ganymede, which has this iron sulfide core. Callisto is believed to be just composed of a rock ice mixture all the way to its core. In 1979, something else was very unusual was observed regarding Jupiter, and that was actually revealed by Voyager. 50,000 kilometers above Jupiter's cloud cover is a very, very thin ring. And this was the first time that a ring had actually been observed around any other object other than Saturn, which was always called the ring planets. We know today, however, that all of the gas giants, all of the outer planets, Jupiter, Saturn, Uranus, and Neptune, all have a ring system around them. So that concludes what I want to say about Jupiter. I mean, there's a lot of other moons, but I don't want to spend too much more time on this.